the goal of the rest of our time together today is to get an introduction to integral calculus. It's the second half of calculus. If you're taking a 2-semester calculus course, this is the second semester's material. For us, it's our second week's material. And what does integral calculus have to do with our marketing project? And then more broadly, how does it relate back to the rest of the calculus that we've been learning about derivatives and so forth? So first I want to talk a little bit about the why. So where do we get a need for integral calculus from in our marketing project, the one that you're working on this semester? Then I'll talk about the what are the different ways of understanding what integral calculus is about? And then finally the how. How do we actually compute, use the tools of calculus to determine the values for integrals? So I want to start back with our demand function again. After decision report 4 in your project, you now know what is the quantity and the price that you want to market your product at because it's going to maximize your profit. That quantity and that price is 1 point on the graph of your demand function. Quantity on the horizontal axis, unit price on the vertical axis. And the idea is we're going to go, at least our initial assumption is that we're going to go out into the market and we're going to charge everybody that same price, whatever that price is. Let's say I'm selling my iPads at $300 per unit. I go out and I charge that same price for absolutely everybody in every market that I sell this product in. The problem with that is that if we charge everybody exactly the same price, aren't we missing out a little bit? Aren't we underpricing our product for some people? Because if you think about it, if I decided to raise my price, there would still be some people, fewer, but still some, that would still be willing to buy. And so if I'm charging everybody that same low price, for a bunch of people, they would have paid more. And as marketing experts, what we'd like to do is somehow tap into that. Right? Tap into people's willingness to pay more than the price that we're ultimately trying to charge the market. So if we didn't, if we just charged everybody the same price across the board, the same flat Q star units sold at P star dollars, then the amount of revenue that we make, revenue is quantity times price, the amount of revenue that we make is just Q star times P star. Right? Let's say I produce 100,000 units, I sell them at $50 a piece, I'm going to be making $5 million in sales revenue. It's just the product of the quantity times the price. But let's think about what that product actually looks like on our demand graph. Q star, the quantity that we're selling, is a number on the horizontal axis, but we can also think of it as a little width along the x-axis. P star, the price, is a little height along the price axis over here. So if I multiply a width times a height, what do I get? I get an area. You thought geometry would have nothing to do with marketing? Ha-ha! Revenue on the demand graph is nothing more than an area. Right? A price times a quantity is the same thing as a width times a height on this graph. Right? And so if I can figure out a way of computing areas on this demand graph, then I have a way of quantifying possible revenues. And by charging everybody the same price, I just get the revenue that's in this single rectangle that's right here. P star times Q star. But because there were some people up here that were willing to pay more for my product, could we possibly tap into that? Could we make some more revenue by charging some people more price than others? Right? And if we could do that, how much extra revenue could we get out of that process? That total amount of extra revenue that's up there is called the consumer surplus. And the goal of our last step in the project is to determine how large that consumer surplus is. If we were to go charging different people different amounts, how much extra revenue could we possibly make out of that? And so, from calculus terms, what we're interested in now are how to compute areas. Specifically, for our project, areas on a demand graph, but more generally, areas on any graph. Areas that are bounded by the graphs of functions y equals f of x that might not be nice straight lines that we can use ordinary geometry to compute. And so the areas that we're going to be able to compute using the second half of calculus, for starters, are going to be areas that are bounded on the top or the bottom by the graph, possibly the really curvy, weird-shaped graph of some function, and are bounded on the other side by the x-axis. So when a mathematician says area under a graph, what they're saying is the area between the graph and the x-axis. And we're going to throw in one more wrinkle into that, that we're going to count that area as either positive or negative, depending on whether or not my graph is above or below the x-axis at that point. So unlike areas in geometry, which are always non-negative quantities, areas in integral calculus can be negative. They're negative when our function is underneath the x-axis. So we call them not areas, but signed areas. Areas that are positive above the x-axis, negative below the x-axis. So those are the kinds of areas that integral calculus will be able to compute for us. And we call those areas the definite integral of this function. So definite integral for us is just going to be a synonym for area. The area under a graph, in other words, between the graph and the x-axis, where that area is counted as positive if the graph is above the x-axis, negative if the graph is below the x-axis. We also have to specify the left and the right-hand boundaries of my area, which are always, for us at least, going to be values of x. So from x equals a to x equals b. That means the area underneath the graph of this function and above the x-axis, between, on the left-hand side, the vertical line x equals a, and on the right-hand side, the vertical line x equals b. So that tells me all of the boundaries of the area that I'm going to be computing with this definite integral. And onto that, as mathematicians always do, we throw some scary-looking notation. And this is how we denote the definite integral of f of x from x equals a to x equals b. So this funny big sign over here, the integral sign, is really just an elongated letter s. It stands for sum, which is actually the way that integrals can be defined. They're defined as the sum. You add up a bunch of little teeny tiny areas and you get the total area. The limits of integration, a and b, that tell me again the left hand and the right hand extent of the region that I'm finding the area of. F of x is the function whose graph is going to define this area for me. And at the end of my notation, I put this little thing called dx, which math majors and mathematicians make a lot of hay out of what this is. For us, we're just going to think of this as the right-hand parentheses in my notation. We can also think of it as saying that x is my variable. You read it as with respect to x. So this just tells me that in my function, f of x, x is the variable that tells me my x-axis. So there's the notation. And this is what integrals are. They're areas. Areas underneath the graph, which are positive if the graph is above the axis, negative if the graph is below the axis. And we'll use that notation to denote them. So that's great. But what does this have to do with calculus? How are we actually going to find one of these areas? Particularly if we can't use ordinary geometry. If my graph happened to be a nice straight line or something, then we could probably just divide up that area into triangles and rectangles and just add those together and use ordinary high school geometry to find the area. But if my graph is a quadratic, well, there's no formula from high school geometry that tells me how to find the area underneath a parabola. And so calculus is what supplies that for us. How do we do it? Well, let's think back to the calculus that we know so far. In our first half of the course, we've talked about how to take a function's value, like a revenue function or a profit function or a demand function, and using a derivative, determine its slopes, its rates of change. Right? So the process of taking a derivative takes me from the value of a function into the slope or the rate of change of a function. And that's great. But we want to know now what calculus has to do with computing areas under graphs. And it turns out, and this is the biggest surprise in an entire semester's worth of calculus, really an entire 2 semesters worth of calculus, the biggest surprise is that that relationship that a function has to its slope is the same relationship that the area under the graph of that function has to the original function itself. In other words, if I take the derivative of a function, I get its slope. If I take the derivative of an area, I get the original function back. So that same derivative relationship relates the area underneath the graph of a function to the value of the function itself. And that's super surprising. That's so surprising that we call it the fundamental theorem of calculus. Okay, so what does that mean about how to compute an area under a graph? Well, what it really means is we're going to be starting with a function. We start with a function under which we want to find the area. So we're starting in the middle. And I want to find an area, which means I have to go from right to left on this diagram, which means I'm not going to be taking a derivative to compute an area. I'm going to be untaking a derivative. I'm going to be going backwards. I'm not going to be finding a derivative. I'm going to be finding what's called an antiderivative. And according to what's on the screen here, we know 2 things. First of all, if you believe me that an antiderivative can do this, if you believe the fundamental theorem of calculus that we're about to talk about, an antiderivative is going to tell us the area under a graph. But even if you don't believe that yet, just based on this little schematic, an antiderivative is supposed to be able to do exactly the opposite of what a derivative does. So one thing that an antiderivative can do is it can reconstruct for me the value of a function from a knowledge of its rates of change. So if I know the slope of a function, I can use an antiderivative to get my function itself back. So one example of where this might happen in a business context is if I might know, let's say, the marginal cost function for something, then I can use an antiderivative to find the total cost. So I can go backwards. Anything I can do with a derivative, I can undo by taking an antiderivative. They're inverse operations to one another. So that's one thing that antiderivatives can do, even if we don't believe the fundamental theorem of calculus. But the one that we came here for does use the fundamental theorem of calculus to compute an area, to compute the value of a definite integral. And here's what the fundamental theorem of calculus tells us. It says that to compute this area, the definite integral from a to b of f of x, I need to do three things. I first need to find the antiderivative for the function f. So whatever the process is to undo a derivative, I'll do that, and I'll get a function which is the antiderivative of little f. The next thing I'll do is I'll evaluate that antiderivative at my two x values, at my right-hand x value and also at my left-hand x value. I'll put the right-hand one first, the left-hand one second. So f of b over here, big F of a over there. And then to get my value for my definite integral, I'll just subtract the former minus the latter. So this fact here in the gray box is what we call the fundamental theorem of calculus. And it's called the fundamental theorem of calculus because it relates together these two seemingly unrelated concepts, the area underneath a graph, represented by the definite integral, and the idea of slopes and rate of change, which is encoded by a derivative. It relates them together because the derivative of my capital F is my little f. So this brings the two halves of calculus together. And for that reason, I think it's called the fundamental theorem of calculus. So if I want to find an area under a graph of a function, take the antiderivative of that function, evaluate that antiderivative at the two endpoints, and then subtract. And that should be all there is to it. And the only remaining step of the how is, how do I actually find an antiderivative? If I know a formula for a function f of x, how do I find an antiderivative for it? Well, as you might expect, it's a process of working backwards. If I know how to take a derivative, I should just reverse my thinking to find an antiderivative. So let's say I have a power like x to the power n. If I were taking the derivative, I would first be multiplying by the exponent n, and then I would be decreasing the exponent by 1. But if I want to do that process backwards, I need to do the opposite of those steps, and I need to do them in the opposite order. So I need to do the opposite of the second step first, and I need to do the opposite of the first step last. All right, so my last step in taking a derivative was to decrease the exponent by 1. What's the opposite of that? Increase the exponent by 1. So that would be the first thing I do when taking an antiderivative of a power. Increase the exponent by 1. The first step in a derivative was to divide by the exponent. So if I'm reversing that, what am I doing? Sorry, I screwed it up. The first step in a derivative was to multiply by the exponent. If I'm reversing that, divide by the exponent. But now the exponent has already been increased by 1. So the exponent I should be dividing by is the new exponent, n plus 1. So if you're looking for a formula for an antiderivative of a power of x to the n's antiderivative is x to the n plus 1 divided by n plus 1. Increase the power by 1, then divide by that new power. And that would get us an antiderivative. But there's a wrinkle. There's a small wrinkle in this process. And that is that this function, f of x equals x to the n, is the same as if I had written x to the n plus 0. Right? If I just add 0 to something, I'm not changing a quantity. So I could have written a 0 there. But 0, even though it doesn't have an interesting derivative, 0 has an interesting antiderivative. What kinds of functions have derivatives equal to 0? So functions whose graphs are horizontal lines will have derivatives of 0. What do functions whose graphs are horizontal lines look like? I mean, what are their formulas? F of x equals just a number, just a constant, exactly. But that constant can be any number. It could be 0. It could be 10. It could be negative pi. It could be square root of 10, right? It could be literally any real number, constant real number, is an antiderivative of 0. Right? And so when I take an antiderivative, if I don't know anything else interesting to tell me otherwise, what I need is this little additive arbitrary constant sitting here at the end of my antiderivative. Right? Because x to the, let's say, 3 divided by 3 plus 10 has the same antiderivative as x to the third over 3 plus 12. Has the same antiderivative as x to the third over 3 minus 62. Right? I can have any arbitrary constant there because when I take the derivative and go backwards, I'm going to get the same original function. Right? So when we just take an antiderivative, we'll include this little arbitrary additive constant plus c at the end, just to hedge, to hedge our bets, to make sure that we're writing down not just an antiderivative, but we're writing down every possible antiderivative for the function x to the n.